So what I'm going to do is, in the time that we have left, I'm going to very, very briefly, at a very high level, go over the standard algorithm for finding solutions to support vector machines. So it's called the SMO algorithm, and we're doing a very, very, very stripped down version of this. So remember, we're trying to find this weight vector, and we've just shown on the previous slide that it's the same thing as finding 2 points, h plus and h minus, such that each point is within h plus is within the positive polytope, h minus is inside the negative polytope, and they're as close as possible to each other. So that's what we're trying to minimize, and it's a constrained minimization problem, which makes things a little bit tricky and finicky. So all the alphas have to be non-negative, and they have to sum up to 1, so that we stay inside the polytope. If you allow, if they don't sum up to 1, then you're going to get outside the polytope, and then you can have all sorts of nonsensical solutions. So that's a form that you may be more familiar with, but they're exactly the same. Okay. So now suppose I have these two polytopes, a set of positives and a set of negatives. The way the algorithm all works, and you start by initializing the alphas, so these are the weights on the positive and the negative centroid in some way, and what I'm going to do is I'm just going to sort of dumbly initialize them to be uniform, right? So I'm placing the positive and the negative centroids at exactly the center of the data. Right? So the positive centroid in this case is going to be, because I only have 3 examples, it's going to be just the center. So I have an alpha of 1/3 for each of the corner points. Now, what the algorithm does then is it does 2 steps. It picks 2 weights, it picks 2 alphas according to some heuristics, and we're not going to talk about the heuristics, but the goal of the heuristics is to come up with the most promising pairs to optimize. And then I'm going to take these 2 weights. So suppose I take alpha 1, which is 1/3, it's a weight on D1, and alpha 3, which is a weight on D3. And now what I want to do is I want to try to tweak these weights as far as I can so that the H point gets H plus gets as close as possible to H minus. But I only get to tweak these two weights. I keep everything else fixed. Okay. By the way, why am I tweaking 2 and not just 1? Can I tweak just 1? I can't, because they all have to sum up to 1, right? So I have to, in fact, I am tweaking 1, but the other one follows. Okay. So now, how can I tweak alpha 1 and alpha 3? The highest possible value to which I can set alpha 1 is 2/3, right? Because the weight on D2 must stay at 1/3. I can't change that. So the best thing I can do is I can completely zero out alpha 3, the weight on D3, and give all of its mass to D1. So that would be a weight of 2/3 on D1 and 1/3 on D2. So that would correspond to a point A that lies right there on the edge between D1 and D2. The smallest I could set alpha to is 0, and if I set alpha 1 to 0, then I'm going to get point B. So it's going to be 1/3 of D2 plus 2/3 of D3. So by changing the alphas, I am looking at all the points that lie on this red segment between points A and B. So that's my red segment, that's my points A and B. Now what I'm going to look for is, I'm going to look at the weight alpha such that when I set alpha to 1, I get the point A. When I set alpha to 0, I get the point B. And I want to find the point, I want to find the alpha that gives me a linear combination that's as close as possible to H minus, the negative centroid, which I'm not touching at the moment, right? So alpha combined with A and B gives me a linear combination of the points A and B, which is going to be just a point on this line. So for example, if I set alpha to 0.5, I'm going to get a point right in the middle. If I set alpha to 0, I'm going to get B. If I set alpha to 1, I'm going to get this. So that equation for an arbitrary alpha defines all possible points on the red line. And what I want to do is I want to find a point that is as close as possible to h minus. So I'm looking at the Euclidean distance, I'm summing up over all dimensions, the Euclidean distance between the linear combination and the point that I'm looking to get close to. And the only thing I can tweak is alpha. You look at that equation, you'll realize that the distance is a quadratic function in terms of alpha. So it's going to be some kind of a parabola. It looks like that. Okay? And for parabola, the nice thing is I can find their minimum. For a parabola in one dimension, you can find their minimum in closed form. So you can just, I don't have to iterate. I don't have to move around. I can just jump directly to alpha that gets me the as close as I can get to h minus. So you take the Euclidean distance, you take a derivative of that, set the derivative to 0, and it turns out that the optimal alpha has just that form. Right? It's a very simple thing. The nice thing about this is you can just compute it very fast. And what this does is this makes the step 2 of the SMO algorithm really, really fast. So you just do it in a fixed amount of time. You don't have to iterate at all. Now that's alpha. So alpha is a linear combination of A and B. And alpha is not really, now I have to take my alpha and map it to the values of alpha 1 and alpha 3, because they had some constraints on them. What you're going to get out of this solution is actually an unconstrained value of alpha star. It could be smaller than 0, and in this particular case it will be smaller than 0, because the closest point along that line is somewhere in here. It's outside of my polytope. I can't allow that to happen, so what I do is I truncate. So if I got an alpha star that was smaller than 0, I'm going to set it to 0. If it was bigger than 1, I'm going to set it to 1. And then I'm going to rescale it by the amount of freedom that I had. Remember, the highest alpha 1 could be is 2/3. So I'm going to multiply this 1 by 2/3. Or if I got an alpha, I just multiply alpha star by 2/3. And that's going to be my value of alpha 1. And alpha 3 is, of course, just 2/3 minus alpha 1. So it's nice. The nice thing about this solution is because it's a parabola in 1D, I don't actually have to solve a constrained minimization problem. I can solve an unconstrained problem, find the absolute minimum, and then truncate it. So if it was under 0, I would truncate it at 0. If it was above 1, I would truncate it at 1. It works for parabola in one dimension, so it won't work in a higher space. Great. So now what does this mean? This means that I have found my alpha 1 and alpha 3, and in this case, the optimal solution is going to be here, where alpha 1 is 0. I'm truncating it to that point. So alpha 1 is going to be 0, alpha 3 is going to be 2/3. So my H plus point is going to move from its starting position, where it was the average of all the points, to that point right there. So I've done that in one iteration, and that iteration involved a closed form solution to a very, very simple equation. So you do that, and then you just repeat the procedure. You pick another pair, you re-optimize the weights, pick another pair, re-optimize the weights.